Welcome to Dark Cosmos Theory. Tonight we embark on a journey through one of the universe's most elegant mysteries. The moon hangs above us, seemingly motionless, its face eternally turned toward our world. For more than 4 billion years, it has maintained this perfect stillness, locked in what scientists describe as tidal synchronization. But this apparent tranquility conceals a story of tremendous forces, gradual transformations, and the patient architecture of gravity itself. We'll unravel this mystery step by step, examining the orbital mathematics, the physics of motion, and the energy exchanges that have frozen our celestial companion in this remarkable equilibrium. This is a narrative written in the language of lost energy, stretched space-time, and the relentless march of cosmic time, quiet, methodical, and profoundly real. Before we begin, if you find value in these explorations of the cosmos, a like and subscription help this channel continue bringing you these journeys through space and time. Now, let us start. The moon appears stationary, or so our eyes tell us. Throughout human history, we've gazed upward at the same familiar patterns, the identical shadows, those unchanging craters forming shapes our ancestors saw and named. But what if this stillness we perceive is actually one of the most intricate gravitational performances in our solar system? The truth is both simple and profound. The moon does rotate, but it does so in absolute harmony with its journey around Earth. This phenomenon, known as synchronous rotation or tidal locking, isn't supernatural or accidental. It's physics, carved by time, sculpted by gravity, and refined by friction across billions of years. Data gathered by NASA's Lunar Reconnaissance Orbiter reveals that the moon completes a single rotation on its axis every 27.3 days, precisely matching the duration of its orbit around our planet. From our terrestrial vantage point, this creates the illusion of a frozen world. In reality, the moon spins at exactly the correct speed to maintain one hemisphere perpetually facing us. To grasp this extraordinary synchronization, picture Earth and the moon connected by invisible gravitational threads. In the moon's early days, approximately 4.5 billion years in the past, shortly after its likely formation from debris created when Earth collided with a Mars-sized protoplanet called Thea, it rotated far more rapidly. Each lunar day might have lasted merely a handful of hours. As countless eons drifted by, Earth's gravitational influence distorted the moon ever so slightly, stretching it into a configuration that departed from perfect sphericity. This minute bulge generated tidal friction within the moon's interior, acting as a cosmic brake mechanism. Gradually, incrementally, the rotation decelerated until it synchronized with the orbital period. At that precise instant, the locking became complete, and from that moment forward, only one face would ever regard our world. NASA scientists refer to this condition as synchronous rotation. It represents a delicate equilibrium where angular velocity, the rate of spin, equals orbital velocity, the speed of travel around Earth. The outcome is captivating. As the moon orbits, it rotates just enough to keep one hemisphere fixed in our direction, like a dancer perpetually facing her partner. We can verify this through mathematics. The moon's mean orbital velocity reaches approximately 1 kilometer per second, and its rotation period of 27.3 Earth days translates to a spin rate of roughly 0.037 degrees per hour. That's extraordinarily gradual, so slow that a complete rotation requires an entire month. This near-perfect alignment isn't unique in our cosmic neighborhood. Numerous moons throughout our solar system share this destiny. Jupiter's Io, Saturn's Titan, and Pluto's Charon are likewise tidally locked, eternally displaying one side to their parent bodies. Yet Earth's moon stands apart because of how precisely it achieved this balance, despite its unusually substantial size relative to Earth. If you've observed the Moon through a telescope and noticed subtle changes at its edges over time, you've witnessed a phenomenon called libration, a gentle oscillation caused by the Moon's slightly elliptical orbit and axial tilt. Thanks to libration, we can actually observe about 59% of the Moon's surface from Earth. Though it appears we only ever see half, this serves as a subtle reminder that even in apparent stillness, there exists motion. Scientists have studied tidal locking not merely through mathematics but also via direct observation. Data from NASA's Grail mission, which mapped the Moon's gravitational field, revealed variations that align with models of internal heating and tidal deformation. These confirm that the locking process isn't just theoretical. It's inscribed in the Moon's very rock. Fractures, stress lines, and variations in crustal thickness all point toward billions of years of gravitational stretching. Dr. James Williams of NASA's Jet Propulsion Laboratory once described this phenomenon simply: tidal locking is nature's method of achieving stability through loss. In other words, as the Moon shed rotational energy, it gained harmony, a stable orbit that has endured for billions of years. But let's make this tangible. Imagine standing on the Moon's near side, the hemisphere we see from Earth. The blue-white marble of our planet hangs motionless in the sky. It never rises. It never sets. It simply hovers there, perfectly still, while stars drift around it. That's what tidal locking means in practice, an eternal view of home. On the far side, though, the hemisphere we never see, Earth never appears. The sky there remains empty of the planet that determined the Moon's fate. There's something haunting about that symmetry. Scientists measure it in terms of angular momentum and energy dissipation. But emotionally, it's the closest thing to cosmic stillness we know. Every crater, every ridge on the near side has faced our planet for billions of years, weathering meteorite impacts while silently reflecting sunlight back to us. Meanwhile, the far side, rougher, older, more scarred, exists in perpetual shadow from our gaze. This perfect alignment has also shaped life on Earth in subtle but profound ways. The Moon's gravitational pull creates ocean tides, stabilizes Earth's axial tilt, and slows our planet's rotation over time. Without this balance, our days might be shorter, our seasons more erratic, and the climate far less stable. So while it might seem like the Moon's lack of spin is a trivial curiosity, it's actually part of the reason Earth's environment has remained hospitable to life. As Neil deGrasse Tyson once observed, the Moon is not just a companion, it's a stabilizer that makes Earth a comfortable home. To the human eye, the Moon's stillness feels peaceful. To the scientific eye, it's a record of motion slowed to perfection, and that's what makes this mystery so captivating. The illusion of immobility is, in truth, the most elegant movement of all. So the next time you see that pale disk glowing in the night sky, remember it's not frozen. It's dancing in perfect silence, spinning and orbiting simultaneously in a rhythm fine-tuned by gravity itself. There is no magic in the heavens, only gravity, relentless and ancient. It doesn't roar, it doesn't flash. Yet for 4.5 billion years, this invisible force has bent worlds to its will, shaping their motion, slowing their spin, and holding them in perfect balance. The Moon is one of its quietest subjects, or perhaps its most perfect creation. To understand why the Moon remains locked, we must look back to the equations that describe nearly everything that moves. Newton's law of gravitation and Kepler's laws of orbital motion. Newton showed us that every mass in the universe attracts every other mass. The force between two bodies, like Earth and the Moon, depends on their masses and the square of the distance between them. The formula F equals G times m1 times m2 divided by r squared looks simple. but hidden inside is a story of energy exchange that spans cosmic time. When the moon first formed, it was spinning much faster, perhaps one full rotation every few hours. That means its surface moved at hundreds of meters per second relative to its center. But Earth's gravitational pull didn't just tug on the moon's surface, it stretched it. This stretching created small bulges, one facing Earth, one opposite. Because the moon was rotating, those bulges didn't stay perfectly aligned with Earth's pull. Instead, they lagged slightly behind the direction of the force. That lag produced tidal friction, an internal resistance that converted rotational energy into heat. According to NASA's Lunar and Planetary Institute, this process acted like a cosmic brake over millions of years. The torque created by Earth's gravity slowed the moon's rotation until the bulges finally aligned perfectly with Earth, at which point the braking stopped. The moon had entered synchronous rotation, locked forever. To put this into numbers, the gravitational torque acting on the moon early in its history might have been around 10 to the 16th Newton meters, enough to heat its crust and mantle. This heat is long gone now, but its geological fingerprints remain: fractures, asymmetric crust thickness, and variations in density that still match the ancient direction of Earth's pull. Scientists today simulate this process using tidal dissipation models, which measure how internal friction converts energy into heat. The moon's rate of energy loss during its early history was likely tens of gigawatts, comparable to thousands of active volcanoes. The result? Its rotation slowed centimetre by centimetre per year until it matched the 27.3-day orbital cycle we observe now. As Dr. James O'Donoghue from JAXA explains, tidal friction is one of the universe's slowest engines, but it always finishes the job. And that job, in this case, was to turn a freely spinning world into one that moves in perfect harmony with its orbit. From a physics standpoint, this process can be described using angular momentum conservation. The total angular momentum of the Earth-Moon system is shared between the Moon's rotation and its orbit around Earth. As friction inside the Moon dissipated energy, angular momentum was gradually transferred from spin to orbit, causing the Moon's rotation to slow and its orbital distance to increase. Even now, the Moon drifts away from us at a rate of about 3.8 centimetres per year, as measured by laser reflectors left by the Apollo missions. It's slow enough to seem eternal, but fast enough that over hundreds of millions of years, the Moon's distance and its effect on Earth's tides will noticeably change. NASA scientists studying tidal effects describe it as the long conversation between Earth and Moon. One pulls, the other resists. The result is equilibrium, but not stillness. It's motion locked in feedback. The same principle applies throughout the solar system. Jupiter's moon Io, for example, experiences such intense tidal forces that it's constantly stretched and squeezed, producing more volcanic heat than any other body in the solar system. Our moon once endured something similar, though gentler. The evidence lies in ancient volcanic plains known as mare basalts, which cooled between 3 and 3.5 billion years ago. These smooth dark regions, visible even to the naked eye, tell us that friction-generated heat once flowed beneath its crust. In short, the moon's lock is not the result of coincidence. It's the inevitable consequence of physics. If you give two massive bodies enough time, friction, and gravitational pull, they'll settle into this exact pattern, one side locked forever. It's an outcome dictated by Newton's mechanics and confirmed by Kepler's second law. Planet-satellite system always seeks the most stable configuration possible. But there's something remarkable about the precision of this lock. The moon's centre of mass is not exactly at its geometric centre. It's offset by about 2 kilometres toward Earth. This asymmetry helps the gravitational grip remain stable. It's as though the moon's own mass distribution was sculpted by billions of years of gravitational stress to maintain the alignment perfectly. Even small oscillations don't break the lock. The balance holds with millimeter accuracy. Modern missions continue to refine our understanding of these forces. NASA's Grail mission mapped the moon's gravitational field in exquisite detail, confirming variations consistent with tidal heating and long-term crustal deformation. The data show that ancient magma once moved in patterns consistent with gravitational flexing, proof that tidal locking wasn't just mechanical, it was geological. Dr. Maria Zuber, principal investigator for Grail, once said, "The moon's gravity field tells the story of a world shaped more by Earth than by itself. That's the heart of this part of our story. The invisible hand of gravity sculpting the moon, not just in orbit, but in structure. Earth and moon are not separate. They are a coupled system, each affecting the other across the gulf of space. When viewed from the outside, say from the perspective of a passing probe, the system looks like a dance frozen mid-turn. Earth spinning rapidly, the moon orbiting slowly, the two locked in a gravitational embrace. But the forces inside are still at work. Earth's own rotation continues to slow, just as the moon's once did. Tidal friction in our oceans dissipates about 3.7 terawatts of energy every year. Eventually, in billions of years, Earth too will become tidally locked to the moon. One side of our planet will always face the moon, the other will never see it again. That's the power of this invisible force. It does not stop. It does not tire. It acts quietly, endlessly, turning chaos into order through loss of motion. As Dr. Carl Sagan once reminded us, gravity is the sculptor of the cosmos. It shapes everything, but it never needs to be seen. So when we look up at the moon and think it's standing still, we're actually seeing the result of 4.5 billion years of gravitational negotiation, a dialogue written in equations, conducted in silence. And yet, even now, this system isn't perfectly frozen. Subtle forces, solar tides, orbital eccentricity, the slow shift of Earth's spin, continue to modify the lock by microscopic amounts. It's a reminder that what looks permanent in the sky is, in reality, dynamic, always changing at scales too small for us to notice. The next time you see the moon, think of this. Every photon of its reflected light, every fraction of its orbit, is the outcome of invisible mechanics, stretching back to the birth of the solar system. The stillness is real, but it's born from struggle, a struggle that never ends. The moon we see tonight looks frozen in time, its face forever unchanged. But billions of years ago, it was not this quiet. It spun rapidly, like a glowing ember torn from Earth, its young crust still molten, its motion wild and untamed. What we now call the locked moon was once a world in motion, rotating freely, its day lasting only a few short hours. To understand how that transformation happened, we must step back to the violent birth of the moon itself. According to the giant impact hypothesis, about 4.5 billion years ago, a Mars-sized protoplanet named Thea collided with the early Earth. The impact released unimaginable energy, enough to melt much of Earth's crust and eject debris thousands of kilometers into space. That debris eventually coalesced, forming the moon. NASA's simulations, confirmed by supercomputer models at the Ames Research Center, suggest that in its first stage, the newborn moon was spinning rapidly, possibly completing one full rotation in less than 10 hours. Its surface was molten from the heat of formation, glowing red-orange and constantly reshaped by the gravitational pull of its parent planet. Over time, that fiery energy began to fade. But gravity doesn't forget. The gravitational tug between Earth and the moon generated tides, not just in our oceans, but within the moon's own interior, creating immense friction that gradually drained its rotational energy. As Dr. James Williams from NASA's Jet Propulsion Laboratory explains, the Moon's rotation slowed because of tidal friction, a process as old as the solar system itself, where energy is never lost, only moved. This friction acted like a cosmic brake, forcing the Moon to exchange its spin for orbital stability. The faster it had spun, the more violently it deformed under Earth's pull. With each rotation, its internal rocks flexed and shifted, producing heat through mechanical stress, the same physics that make Io, Jupiter's volcanic moon, so active today. But while Io vents that heat through eruptions, the Moon's smaller mass couldn't sustain such energy release. Instead, it cooled, stiffened, and slowly came to rest. According to data published by the Lunar and Planetary Science Institute, early tidal interactions between Earth and Moon released up to 10 to the 19th joules of energy, enough to power modern civilization for millions of years. That immense amount of energy didn't vanish. It was absorbed as heat and deformation inside the Moon, changing its structure forever. As the lunar crust thickened, tidal deformation became harder. Friction continued to act, but its effect diminished as the Moon's mantle cooled and solidified. By around 100 million years after formation, scientists believe the Moon's rotation had slowed enough that it was nearly synchronized with its orbit, one side constantly pulled toward Earth, the other turning away into permanent darkness. The process didn't happen evenly. NASA's SMART 1 mission, which mapped the Moon's surface composition, revealed clear differences between the near and far sides. The near side, the one we see, has thinner crust, smoother plains, and large basaltic maria created by ancient lava flows. The far side, on the other hand, has a thicker crust and more impact craters. This asymmetry isn't random. It's a fossil record of how the Moon's rotation slowed unevenly under Earth's pull. Dr. Maria Zuber from the Grail mission summarized it beautifully in one sentence. The Moon's shape is a memory of its motion, and that memory is measurable. Using data from lunar laser reflectors placed by the Apollo 11, 14, and 15 astronauts, scientists have determined that the Moon's orientation has been stable for at least billions of years, wobbling only slightly by a few arc seconds due to libration effects. These tiny oscillations are the leftover tremors of a world that once spun freely. If we could rewind time, the young Moon's sky would look nothing like what we know today. An observer standing on its molten surface, if one could survive, would have seen Earth racing across the heavens, rising and setting rapidly every few hours, surrounded by a haze of vaporized rock. The tides on both bodies would have been colossal, forces so great that the crust itself may have cracked and reformed multiple times. NASA's 2023 high-resolution simulations show that the Moon's early rotation period and orbital distance changed in tandem. As it slowed, its orbit expanded, just as it continues to do today. This outward drift, currently measured at 3.8 centimeters per year, is the long-term echo of that same ancient braking. Every centimeter represents lost spin converted into distance. This process isn't unique to the Moon. Astronomers have found similar signatures across the solar system. Pluto and Charon, for instance, are mutually tidally locked, each showing only one face to the other. Mercury rotates 3 times for every 2 orbits around the Sun, caught in a partial resonance known as a 3.2 spin-orbit lock. These examples confirm that tidal forces are universal and inevitable wherever gravity and motion coexist long enough. For the Moon, the final synchronization likely occurred about 3 to 3.5 billion years ago. Since then, its rotation and orbital periods have matched almost perfectly. The once dynamic world became what we see now, serene, still, yet forever in motion around us. The paradox is stunning. The moon's stillness is not the absence of movement, but the result of perfect balance between two opposing energies, inertia and gravity. Inside the moon, evidence of this transition remains. Grail's data show fossilized stress lines and density variations deep in the crust that correspond to ancient tidal flexing. These are physical scars of the breaking process, geological proof that the moon once spun far faster than it does today. If you imagine time-lapse footage of that history, it would be like watching a spinning top slow under invisible friction. The motion doesn't stop instantly. It wobbles, stabilizes, and finally turns in perfect sync with the rhythm of its surroundings. That's what the moon did, only over millions of years. In scientific terms, the moon's rotational kinetic energy decreased while its orbital angular momentum increased. The total angular momentum of the Earth-Moon system remained constant as Newton's laws demand. But within that constancy, motion was redistributed. Rotation transformed into orbit. The result was not chaos, but equilibrium. Dr. Neil deGrasse Tyson once said, "In space, everything moves toward balance, and balance is never truly still. It's this balance that explains why the moon appears frozen. What we're witnessing is not a lack of motion, but the completion of a long evolutionary process, one governed entirely by physics. When the last fragments of internal heat escaped and the mantle fully cooled, the moon's face toward Earth was set forever. The synchronization became self-reinforcing. Any attempt to rotate slightly out of alignment would create a restoring torque, pulling it back. The system found its minimum energy state, a configuration that has lasted for billions of years. From a scientific standpoint, that is one of the most stable relationships known in planetary mechanics. It's so stable that even after billions of impacts, quakes, and shifts, the moon continues to keep its orientation within a fraction of a degree. Yet, if we could have seen the moon in those first few 100 million years, glowing, spinning, shedding its heat into space, we'd have witnessed a completely different world. A world that moved, changed, and evolved under the watch of gravity's invisible hand. It's easy to think of the moon as static, but it carries within it the record of motion, a fossil of energy transformed. And though it no longer spins freely, the trace of that freedom is written in its crust, its orbit, and its constant silent pull on Earth's tides. The next time you look up, remember that the face you see has not always been the same. It's the survivor of motion, the remnant of a world once dynamic, now in perfect restraint. For thousands of years, humanity looked up at the same silver face, never once seeing its far side. It wasn't until 1959 that the veil finally lifted, not through a telescope, but through the lens of a small Soviet spacecraft called Lunar 3. That year, for the first time in human history, we saw what no eye on Earth had ever seen, the far side of the moon, strange, scarred, and utterly different. The discovery was shocking. The Lunar 3 probe, launched by the Soviet Union, captured 29 photographs of the hidden hemisphere as it orbited behind the moon. Those grainy black and white images, transmitted over 400,000 kilometers back to Earth, revealed a landscape so alien that scientists at the time could hardly believe it was part of the same world. The far side was dominated by impact craters, deep basins and rugged highlands. Missing were the familiar dark patches we see from Earth, the vast lava plains known as Maria, or seas. For centuries, astronomers had imagined the moon as symmetrical, two similar faces divided only by shadow. Lunar 3 destroyed that illusion. The near side, facing Earth, is smooth and marked by dark basaltic plains, the remnants of ancient volcanic floods. The far side, by contrast, is mountainous, thicker in crust, and far older in appearance. As NASA's Lunar Reconnaissance Orbiter later confirmed, This difference is not just visual, it's geological, chemical, and historical. According to LRO data, the Moon's crust on the far side averages 15 kilometers thicker than the near side. This extra thickness likely prevented large-scale lava flows from surfacing there billions of years ago. On the near side, thinner crust allowed magma from the Moon's mantle to reach the surface, filling ancient impact basins with dark basalt and creating the Maria. The far side, by contrast, remained locked in its primitive cratered form, a record of impacts that stretch back to the early solar system. SMART 1 mission and NASA's Clementine probe both confirmed that the chemical composition differs sharply between the two hemispheres. The near side is rich in iron and titanium, while the far side is dominated by lighter elements like aluminum and calcium. These findings suggest that the Moon's internal heat distribution was never even, perhaps because Earth's gravitational pull influenced its early cooling. As Dr. Noah Petro, a scientist from NASA's Goddard Space Flight Center, explains, Earth's presence likely concentrated radioactive heat-producing elements on the near side, leaving the far side colder and thicker. That imbalance changed everything. When meteorites bombarded the young Moon, a period scientists call the Late Heavy Bombardment, around 4.1 to 3.8 billion years ago, the near side's thinner crust allowed molten lava to rise and heal some of the scars. The far side could not. Every crater that struck there remained, fossilized in rock, untouched by time. The largest of these scars is the South Pole Aitken Basin, one of the biggest known impact structures in the solar system. It spans roughly 2,500 kilometers and reaches depths of up to 8 kilometers. Formed more than 4 billion years ago, it is so vast that if you could stand inside, its walls would curve beyond the horizon. Data from NASA's Grail mission shows that this basin punched through much of the Moon's crust, possibly exposing materials from the mantle, a rare glimpse into the Moon's inner composition. When the Lunar Reconnaissance Orbiter began mapping the Moon in 2009, it gave us the first high-resolution global view of this mysterious hemisphere. Its narrow-angle camera, capable of imaging details smaller than a meter, revealed a landscape that looks almost like a frozen storm. Endless craters overlapping, ejecta rays stretching hundreds of kilometers, ridges and valleys shaped by billions of impacts. Some regions, like the Tsiolkovsky crater, even show signs of past volcanic activity, a hint that the far side wasn't entirely dormant. But these are rare exceptions, not the rule. The far side's surface temperatures, measured by LRO's Diviner radiometer, can drop below minus 230 degrees Celsius during lunar night, colder than any point on Earth. Without the direct warmth of reflected sunlight from Earth, this hemisphere experiences deeper and longer freezes. It is a world of perpetual shadow and silence. Dr. Mark Robinson, principal investigator of LRO's camera system, once described the view in precise but haunting terms. The far side is a geological museum. Nothing erases history there. Every crater, every ridge, every dust grain holds a record of ancient collisions that shaped not only the Moon, but the early solar system itself. Because the far side has remained geologically inactive for billions of years, it serves as a time capsule, preserving conditions from an era long erased elsewhere. Modern missions have continued where Lunar 3 began. In 2019, China's Chang'e 4 became the first spacecraft to land softly on the far side of the Moon, in the von Karman crater inside the South Pole Aitken Basin. Its rover, U-22, continues to send back data about the mineral composition and subsurface structure of the region. The results show materials rich in olivine and low calcium pyroxene, minerals that may come from deep within the Moon's mantle, confirming predictions made decades earlier by NASA scientists. What's most striking, however, is not what the far side contains, but what it lacks. There are no seas, no broad plains, no volcanic scars comparable to Mare Imbrium or Mare Tranquillitatis. There are no dark spots visible from Earth. It is, in the truest sense, a different moon. This contrast has practical consequences for exploration. Because the far side always faces away from Earth, it is shielded from our planet's radio interference, making it one of the quietest places in the solar system for radio astronomy. NASA and ESA have both proposed future missions to place radio telescopes on the far side's surface to listen for faint signals from the early universe, potentially detecting radio emissions from the first stars that formed after the Big Bang. The far side's isolation makes it perfect for science, but also difficult to reach. Without direct line-of-sight communication, spacecraft must rely on relay satellites orbiting above the Moon to transmit data back to Earth. China's Queqiao satellite, launched in 2018, currently performs this role for Chang'e 4, orbiting the second Earth-Moon Lagrange point, L2, to maintain a constant connection. This marks a technological milestone. For the first time, humanity has a stable link to the hemisphere we once thought untouchable. If we could stand on the far side tonight, the sky would look almost unrecognizable. Earth would never rise. The stars would blaze unfiltered by atmosphere or reflection. The Milky Way would stretch across the sky with brutal clarity. The silence would be absolute. Every step would echo across a landscape untouched for billions of years. And yet all of it, the craters, the cold, the desolation, is the direct result of one fact: the Moon's tidal lock. Because the far side always faces away from Earth, it has spent billions of years exposed to the full force of meteoroid bombardment. Earth's gravity shields the near side slightly, sweeping up debris that would otherwise strike it. The far side, without that protection, bears the scars of everything the Earth-Moon system ever encountered. It's a brutal symmetry. The side we see is calm, familiar, and bright, the face of the Moon that shaped human myths. The hidden side is its history, raw, unprotected, and ancient. Both are parts of the same body, but each tells a different chapter of the same 4.5 billion year story. Dr. Neil deGrasse Tyson summarized it best. The far side of the Moon is not dark, it's just unseen. What hides from our eyes still shapes our world. That unseen world continues to draw scientists, explorers, and dreamers alike. The data from Lunar 3 and LRO didn't just reveal a new face of the Moon. They redefined our understanding of how planets evolve under the relentless hand of gravity and time. Every second, the Moon drifts away from Earth about 3.8 centimeters, or roughly 1.5 inches each year. That may sound insignificant, but across millions of years it changes everything. It means that even now, the ancient gravitational handshake between Earth and Moon isn't over. The forces that once locked the Moon's rotation are still active, still pulling, still transferring energy across the gulf of space. This slow drift, first measured precisely by laser reflectors left on the lunar surface during NASA's Apollo missions, is one of the most delicate and revealing observations in celestial mechanics. When Apollo 11 astronauts placed the Lunar Laser Ranging Retroreflector on the Moon in 1969, scientists began firing laser pulses from Earth and measuring how long they took to return. The results showed that the distance between Earth and the Moon increases by nearly 3.8 centimeters every year, a direct result of tidal friction. So what is tidal friction? It's the same invisible process that slows Earth's rotation and keeps the Moon locked in place. But it hasn't stopped working. Even now, Earth's gravity pulls on the Moon, raising slight tidal bulges in its solid body, just as the Moon's gravity raises tides in our oceans. These bulges never line up perfectly with the centers of attraction. Instead, because both Earth and Moon rotate, the bulges are always a little ahead or behind, creating torque, a twisting force that transfers energy from rotation to orbit. In this case, energy flows from Earth's spin into the Moon's orbit. As a result, Earth's rotation gradually slows down by about 2 milliseconds per century, while the Moon's orbit grows larger. NASA's Jet Propulsion Laboratory describes it as a conservation trade-off. The total angular momentum of the Earth-Moon system is constant. What Earth loses in spin, the Moon gains in distance. This process is still measurable today. Modern lunar laser ranging experiments, operated by observatories such as the Apache Point Observatory, Lunar Laser Ranging Operation, Apollo, in New Mexico, have reduced the uncertainty of these measurements to a few millimeters. The data perfectly match predictions made by Newtonian and Keplerian models of tidal interaction, a slow but relentless exchange of motion that continues even after billions of years. To visualize this, imagine Earth's oceans as massive mobile brakes. The gravitational pull of the Moon creates two tidal bulges on opposite sides of our planet. Because Earth rotates faster than the Moon orbits, those bulges are always slightly offset, ahead of the Moon. That offset exerts a small forward pull on the Moon, giving it more orbital energy and pushing it into a higher orbit. Meanwhile, the same interaction drags on Earth's rotation, making our days imperceptibly longer. It's a system in perfect balance, but one that never truly rests. According to NASA's Goddard Space Flight Center, Earth's day lengthens by about 1.7 milliseconds per century. At that rate, hundreds of millions of years from now, a day on Earth will last more than 25 hours. What's extraordinary is that this same mechanism that once froze the Moon's spin now continues to modify the system in subtler ways. Though the Moon's rotation is already locked to Earth, the gravitational coupling hasn't reached a complete stop. It's still extracting energy from the system, not enough to alter the lock, but enough to change the orbit over geological timescales. This means the Moon's distance, its orbital period, and even its inclination will continue to evolve. Astrophysicists describe it as gravitational aging. As the Moon drifts outward, its orbital speed decreases, currently about 1 kilometer per second, but gradually slowing as its distance increases. The farther it goes, the weaker the tidal forces become, which in turn slows the rate of drift. The process will eventually reach equilibrium billions of years from now, when both Earth and Moon are tidally locked to each other, each showing the same face forever. When that happens, the Earth-Moon system will be a pair of synchronized worlds, Earth rotating once for every lunar orbit, the Moon fixed above one hemisphere of our planet, never rising or setting. Dr. Jack Lissauer, a planetary scientist at NASA's Ames Research Center, notes, "It's not just the Moon that's being locked. Earth is heading toward the same fate. It's a slow dance of mutual capture. Until then, the gravitational friction continues to shape our planet in ways we can measure through tides, energy dissipation, and small but cumulative rotational changes. Every ocean wave, every high tide contributes infinitesimally to the Moon's escape. Scientists estimate that about 3.7 terawatts of power, nearly the total global human energy consumption, is dissipated as heat in Earth's oceans due to tidal friction. It's an immense amount of energy, lost silently, spread across billions of square kilometers of moving water. But that energy doesn't vanish. It becomes orbital momentum, gently pushing the Moon farther from us each year. So is Earth's gravity still killing the Moon's spin? Not exactly. The Moon's rotation is already synchronized, so it no longer slows relative to its orbit. But the same gravitational system that created that lock continues to extract energy from Earth's faster rotation, keeping the balance dynamic. The Moon's spin isn't dying. It's settled into perfect harmony, a state maintained by constant microscopic adjustments in orbital distance and speed. The evidence for this comes not only from modern instruments, but also from fossilized tidal records on Earth. Sedimentary layers known as tidal rhythmites, found in ancient rocks, preserve patterns of high and low tides over hundreds of millions of years. These records show that 400 million years ago, a day on Earth lasted about 21.9 hours, and there were roughly 420 days in a year. That aligns perfectly with the laser data we see today, proof that the Moon's slow drift outward has been steady and continuous since the time of the first life on land. The physics behind this is simple, but the consequences are immense. Tidal forces are one of the most powerful natural mechanisms for transforming energy in the universe. They shape galaxies, tear apart comets, and determine the spin states of planets and moons. On Earth, they moderate the oceans, stabilize our climate, and may even have influenced the evolution of coastal life. The same gentle pull that creates our tides is the one that sculpted the Moon's orbit, and that connection, across 384,400 kilometers, never ceases. NASA scientists often describe it as a conversation in gravity, a constant exchange of energy and momentum between two bodies locked in orbit. As Dr. Neil deGrasse Tyson put it, tides are proof that even across the void, the Earth and Moon are still touching. That statement is scientifically precise. Though space between Earth and Moon is vast, their gravitational fields blend seamlessly. Each exerts measurable influence on the other, not metaphorically, but physically, through acceleration, stress, and deformation. The Moon's mass distorts Earth's oceans. Earth's pull deforms the Moon's crust. Each tug, each oscillation is part of a continuous feedback loop, billions of years old. We often think of the Moon's stillness as permanent, but these measurements reveal it as part of a living system. It's a dynamic equilibrium, not static, but stable through constant change. The same equations that govern satellites and space stations also govern this relationship: Newton's law of gravitation, Kepler's laws of motion, and the conservation of angular momentum. Together, they form the invisible framework that holds our night sky in place. ESA's future Lunar Pathfinder mission, along with NASA's upcoming Artemis program, will continue to refine these measurements, offering even more insight into how the Moon's orbit evolves and how long this slow drift will last. Some models predict that in about 50 billion years, the system will reach total tidal locking, long after the Sun has expanded into a red giant. Until then, we live in the transitional era when the Moon is still pulling away, Earth still spinning faster, and the balance between them still changing. Every night sky we see is a snapshot in that ongoing story. The tides that shape our shores are the visible signature of that ancient process, continuing quietly as they always have. In truth, Earth's gravity isn't destroying the Moon's motion. It's refining it, guiding it towards stability 1 inch at a time. And as that distance slowly widens, our planet's own rhythm changes with it, proving once more that nothing in the universe truly stands still, not even the bond between Earth and its oldest companion. What if tonight something jolted the Moon? A hidden force, a massive impact, a celestial mistake, and it began to spin again? What if that silent grey disk, so perfectly balanced for billions of years, suddenly broke free of Earth's gravitational lock? This is not science fiction. It's a scenario astrophysicists have modelled, and its consequences would ripple through the solar system in ways both beautiful and catastrophic. Let's start with what we know. The Moon's tidal lock with Earth is not just coincidence. It's a delicate equilibrium between rotational energy, gravitational torque, and orbital mechanics. If that balance were broken, the first thing to go would be Earth's tides. Right now, the Moon's gravity pulls on Earth's oceans, raising high and low tides that shape coastlines and climate systems. This gravitational rhythm helps regulate ocean currents, temperature gradients, and even wind circulation. If the moon suddenly spun faster, even slightly, its tidal bulges would shift unpredictably. The timing and magnitude of tides would change from day to day, potentially causing coastal flooding in some regions and dead tides in others. NASA's Goddard Space Flight Center explains, the tides are not just oceanic, they're planetary. They affect how energy moves through the entire Earth system. In short, changing the moon's spin changes Earth's energy flow. But that's only the beginning. If the moon began rotating freely again, its mass distribution would also shift. Over time, the moon's internal structure, its solid crust, semi-molten mantle, and small metallic core has settled into equilibrium under tidal forces. A sudden reintroduction of spin would generate massive internal stress. The crust could crack, releasing stored energy from billions of years of compression. The far side, thick and rigid, might fracture more violently than the near side. Lunar geodynamics models predict that even a 10% increase in rotational velocity could create seismic waves strong enough to shake the moon's entire structure. These so-called moonquakes, already recorded by Apollo-era seismometers, would multiply dramatically. NASA's Apollo 17 instruments once detected shallow moonquakes with magnitudes up to 5 on the Richter scale, triggered only by tidal flexing. If rotation returned, those tremors could climb much higher. The moon's surface, now silent and still, might begin to crumble. Dust would shift. Loose regolith could slide down crater slopes. Centuries of stable sunlight and shadow patterns would vanish. The once constant face of the moon would start to change. But the most dangerous effects wouldn't happen there. They'd happen here on Earth. The moon acts as a stabilizer for Earth's axial tilt, keeping it at about 23.5 degrees. That tilt gives us our seasons and maintains relatively predictable climate cycles. If the moon's rotational state changed, its gravitational coupling with Earth's equator would weaken. Over long timescales, the tilt could begin to wander chaotically. Without the moon's steadying influence, Earth's axis might swing wildly between 10 and 45 degrees. As computer simulations by NASA's Ames Research Center have shown, such changes would drastically alter solar exposure across latitudes. Polar ice would melt and refreeze in unpredictable cycles. Deserts could become fertile. Tropical regions could freeze. Day length would fluctuate slightly as angular momentum shifted between Earth and Moon. The stable rhythm that's governed our planet for eons would fracture. Imagine for a moment an Earth without predictable tides, seasons, or nights. The Moon, once our cosmic metronome, would become an unpredictable companion, rotating independently, its surface changing with every evening. We would no longer see the same man in the moon. Each night a new face would rise, a new pattern of shadows, a new geometry of craters. Lunar eclipses would appear distorted, unpredictable, and less frequent. The moon's brightness might fluctuate as different terrains reflected sunlight differently. To astronomers, it would be a nightmare of orbital recalculations. To life on Earth, it would mean profound instability. But how could this happen? What could possibly make the moon spin again? Theoretically, it would require a massive external torque, something large enough to overcome the moon's gravitational synchronization with Earth. A major asteroid impact, perhaps tens of kilometers across, could do it. However, as NASA's Near-Earth Object Program confirms, such collisions are extraordinarily rare. Still, they've happened before in the solar system. Mercury's slow rotation, for instance, may have been influenced by ancient impacts that altered its spin rate and orbital resonance. If a similar event struck the moon, the shockwave could shift its angular momentum. The immediate effect would be catastrophic on its surface, ejecta raining down across space, debris potentially reaching Earth's upper atmosphere. But even if the spin change were small, over time it would destabilize the gravitational coupling that keeps our tides and seasons stable. NASA's current lunar gravitational models show that just a 1% change in the Moon's rotational period could increase tidal stress on Earth by up to 15%, enough to alter oceanic circulation. The resulting chain reaction could disturb Earth's climate systems and atmospheric dynamics for centuries. Planetary scientist Dr. Hakan Svedhem once described the Earth-Moon system as a gravitational pendulum tuned over billions of years. Any sudden push breaks the rhythm, and chaos follows. That's exactly what would happen. Beyond climate and tides, there's also orbital stability to consider. The Moon's perfect lock helps keep its orbital plane and eccentricity consistent. A spinning Moon would slowly alter its own gravitational distribution, known as its mass quadrupole moment, which could perturb its orbit over thousands of years. This could make its path around Earth slightly more elliptical, as the distance between Earth and Moon varied more dramatically. The strength of tides and night illumination would fluctuate cyclically. It's not immediate destruction, it's instability. And instability in celestial systems has a way of growing over time. But perhaps the most profound consequence would be the loss of equilibrium itself. The Moon's lock is the reason Earth's rotation and orbit have remained steady enough for life to evolve. Without it, the interplay of gravitational and rotational forces would no longer produce the calm cycles our biosphere depends on. The Moon's stillness, it turns out, is not just aesthetic, it's structural. It keeps our world's geometry predictable. It keeps energy exchange between Earth, atmosphere, and ocean finely balanced. It keeps chaos at bay. Dr. Neil deGrasse Tyson once said, "Without the Moon, Earth would be a restless planet, wobbling, swaying, never sure of its balance." That observation captures the truth behind this scenario. The Moon's motion, or lack thereof, is not trivial. It's the framework on which Earth's climate stability hangs. So if the Moon spun again, we wouldn't just lose the same familiar face in the sky. We'd lose part of the equilibrium that makes Earth habitable. Seasons would shift unpredictably, tides would destabilize, and long-term climate cycles might collapse. The oceans, the atmosphere, and even the biological rhythms of countless species, all of them tuned to the steady lunar cycle, would begin to drift. This is why astronomers describe the Earth-Moon relationship as a cosmic anchor. The tidal lock is not a limitation, it's a safeguard. It prevents extremes. It holds the Earth steady, while the rest of the solar system spins through its violent history. If we could see this through time-lapse, the Moon suddenly freed, turning faster, the tides shifting, Earth's axis trembling, it would look like a dance gone wrong, elegant steps turned chaotic. But nature abhors instability. Given enough time, the same forces that locked the Moon once before would likely act again. Tidal friction would return, energy would drain, and the system would eventually resynchronize, though at a new distance, perhaps millions of kilometers farther away. In that sense, even if the Moon began spinning again, the laws of physics would slowly correct it. The lock might take tens of millions of years to re-establish, but gravity always finds the path of least energy. It would restore the rhythm, one cycle at a time. The stillness we see in the night sky, then, isn't weakness, it's strength. It's the natural endpoint of cosmic negotiation, the balance that comes when two worlds finally stop fighting against motion and choose stability. We call the Moon still, but it never truly is. Even now, while it seems frozen in the night sky, it's quietly rocking, tilting, and breathing through space in tiny rhythmic motions. This subtle dance is known as libration, and it allows us to see 59% of the lunar surface from Earth, not just half. To the naked eye, the moon looks fixed, its face always turned toward us. But NASA's precise measurements reveal that it moves ever so slightly, shifting back and forth, up and down as it orbits Earth. These oscillations, caused by the moon's elliptical orbit, axial tilt, and orbital geometry, make it appear to nod and sway as though it's gently breathing. There are three main types of libration, each born from the exact laws that govern planetary motion, the same equations written by Johannes Kepler and refined by Isaac Newton centuries ago. They are called libration in longitude, libration in latitude, and diurnal libration. Together they make the moon's apparent motion more complex and more beautiful than our eyes can perceive unaided. Let's start with libration in longitude, the most significant. Because the moon's orbit around Earth is not a perfect circle, but an ellipse. It travels faster when it's closer to Earth, perigee, and slower when it's farther away, apogee. However, its rotation rate remains nearly constant. This mismatch causes a subtle effect. As the moon races through the nearer part of its orbit, its spin can't quite keep up, letting us peak slightly around one edge. When it slows on the far side of its orbit, its rotation overtakes the orbital motion a bit, revealing the opposite limb. The result? From Earth, we can see about 8 degrees beyond each edge, a total of roughly 16 degrees of side-to-side rocking. NASA's Lunar Reconnaissance Orbiter has confirmed this through laser altimetry and long-term imaging. The edges of the moon drift cyclically over a 27.3-day period, creating what astronomers describe as a slow, graceful oscillation of its visible face. Next comes libration in latitude. This happens because the moon's axis is tilted by about 6.7 degrees relative to its orbital plane. As the moon orbits Earth, this tilt makes us alternately see slightly over its north pole and then under its south pole. Over the course of a month, this up and down movement exposes an additional 6 degrees of lunar territory. That's why if you observe the moon carefully night after night through a telescope, you'll notice that its poles seem to lean toward and away from you, a subtle but measurable nod. Finally, there's diurnal libration, the smallest but still significant. It's caused not by the moon itself, but by our position on Earth. As our planet rotates, an observer at sunrise views the moon from a slightly different angle than the same observer at sunset. This shift, only about 1 degree, adds a faint parallax effect that lets us glimpse a bit more of the lunar edges. Add all of these together, and the illusion of perfect stillness dissolves. In truth, the moon moves through a complex pattern of oscillations, exposing different regions at different times. That's why detailed lunar maps, compiled by missions like LRO, Kaguya from JAXA, and Clementine, include features we never see all at once, features only visible during the extremes of libration. To measure these movements, scientists use laser altimeters, radio tracking, and stereoscopic imaging. The LRO's Lunar Orbiter Laser Altimeter, for example, can detect height changes as small as 10 centimeters, tracking how the moon's apparent orientation shifts with incredible precision. These data have revealed that the amplitude and frequency of libration are influenced by not only orbital mechanics, but also mass concentrations, or mascons, within the lunar crust, regions of higher density left behind by ancient impacts. NASA's SMART 1 mission and NASA's Grail mission both found that these mascons subtly distort the moon's gravitational field, slightly altering its spin and orbital motion. Over long timescales, they even affect how the moon's libration evolves. In other words, the moon's rocking is not perfectly periodic. It changes very slowly as the moon's internal structure cools and as its orbit drifts outward from Earth. Dr. Richard Gross, a geophysicist at NASA's Jet Propulsion Laboratory, described it this way: "The moon's motion is a mirror. It reflects not only gravity's pull, but the history of its interior. If we could accelerate time, the moon would appear to pulse, to inhale and exhale through gravitational motion, its face tilting and twisting in long, slow breaths. These librations are small, but their precision helps scientists probe the moon's deep interior. By studying tiny irregularities in how it moves, researchers can estimate the size and composition of the moon's core, which is believed to be about 530 kilometers in radius and composed of partially molten iron. In fact, data from NASA's Lunar Prospector and Grail missions suggest that the moon's core still contains a liquid outer layer, and that its slight wobble or physical libration changes subtly as this fluid interacts with the solid mantle above it. This means the moon's movement isn't just external, it extends all the way to its heart. That's why the moon's librations are so valuable to planetary scientists. They are natural seismographs, transmitting information about the unseen. Each tiny motion, a shift of fractions of a degree, tells us about viscosity, density, and the evolution of the lunar crust and mantle. The precision with which we can now measure these effects is astonishing. Using very long baseline interferometry, VLBI, a technique that links radio telescopes across continents, astronomers can pinpoint the moon's position to within a few centimeters. These observations show that its libration patterns are stable, predictable, and consistent with models of gravitational locking that include minute perturbations from the sun's gravity. Even the sun contributes a faint influence. As the Earth-Moon system orbits the sun, solar tides induce small variations in orbital velocity and distance, slightly modulating the libration angles. These subtle effects, measured over decades, help scientists refine our understanding of how three-body gravitational systems behave over long timescales. Dr. Noah Petro of NASA summed it up simply: "The moon is in constant motion. It only looks still because we live too slowly to see it move." And that, perhaps, is the most haunting truth about our nearest celestial neighbour. Its apparent stillness is an illusion of human timescale. The moon is rotating, orbiting, oscillating, precessing, moving in ways that unfold over weeks, years, and eons. If we could speed up time, we would see it spinning like a slow pendulum, orbit widening, poles nodding, surface flexing. It would not look silent at all. In that silence, however, there is precision, a balance so perfect that it almost feels alive. Every oscillation, every tiny adjustment keeps the Earth-Moon system stable. Without libration, our gravitational coupling might grow rigid and brittle. With it, the system breathes just enough flexibility to maintain equilibrium. As NASA's data shows, the moon's oscillations are decreasing at an infinitesimal rate. The system is still fine-tuning itself after billions of years of evolution. It's the ultimate demonstration of physics in harmony: rotation, orbit, mass, and gravity working as one. And so the next time you see the moon hanging still in the night sky, remember it isn't frozen. It's moving softly and silently in ways the human eye cannot follow. Its face tilts and wavers. Its poles bow and rise. Its distance breathes in and out by inches, all governed by forces older than life itself. As Dr. Carl Sagan once said, "Even in silence, the universe keeps time." The moon, then, is not still. It's simply too precise to notice. It turns, it sways, it drifts in the rhythm of gravity's quiet music. It shouldn't have been this perfect. In a solar system filled with chaos, with worlds spinning at different rates, colliding, drifting, and breaking apart, somehow Earth and its moon ended up locked in a flawless gravitational rhythm. How did that happen? Was it pure chance? Or was there something inevitable written deep into the laws of motion that made this balance unavoidable? To understand the mystery, we first have to look beyond Earth, across the solar system, to see whether this so-called tidal lock is really rare. Surprisingly, it isn't. Of the more than 290 known moons orbiting planets in our solar system, a large fraction are tidally locked to their host worlds. Io, Europa, and Ganymede around Jupiter, Titan, Enceladus, and Rhea around Saturn, Charon around Pluto, each of them shows one face to its planet forever. So in one sense, tidal locking is a natural outcome of gravity's persistence. But here's what makes our moon unique: its size. Earth's moon is enormous compared to its parent planet, about 27% of Earth's diameter and 1.2% of its mass. For comparison, Jupiter's biggest moon, Ganymede, is only 4% of Jupiter's diameter. Statistically, that makes the Earth-Moon pair an anomaly, almost a double planet rather than a planet and its satellite. NASA's Goddard Institute for Space Studies notes that this mass ratio is unusually high among known planet-moon systems, meaning that the moon's gravitational influence on Earth is stronger than any other satellite's influence on its host. This relationship allowed the two bodies to exchange angular momentum more efficiently, bringing them into synchronization far faster than smaller moons could achieve. Dr. James Williams from NASA's Jet Propulsion Laboratory put it plainly: the Earth-Moon pair is locked not because it's special in mechanism, but because it's special in proportion. That proportion, that balance of size, distance, and mass, is what makes the lock so perfect. Early in the solar system's history, tidal locking was common, but the details of each lock varied. Some moons, like Mercury, never fully synchronized. Instead, Mercury spins 3 times for every 2 orbits around the Sun, what scientists call a 3.2 spin-orbit resonance. Others, like Pluto and Charon, locked each other completely, both showing the same face forever, rotating together like a single frozen duet. Earth and Moon are somewhere between those extremes, one body spinning much faster, the other already locked, the two slowly evolving toward an even deeper balance. This delicate in-between state is what keeps our days and nights stable, our tides rhythmic, and our planet's axial tilt steady. To see how improbable this balance is, astronomers run statistical simulations using orbital dynamics models. They plug in random starting conditions, distances, masses, rotation speeds, and simulate millions of hypothetical planet-moon systems. In most cases, either the moon falls inward and crashes into its planet, or drifts away so far that it escapes entirely. Only a narrow range of parameters produces a long-term stable tidal lock, and Earth's moon falls right inside that range. Not just stable, but optimally stable. NASA's Planetary Systems Division described it in 2023 as a natural coincidence amplified by scale. The moon's formation through a giant impact gave it the exact combination of mass and distance needed to reach synchronization within a few billion years, not too fast, not too slow. If it had been smaller, the locking torque would have been weaker. If it had been farther away, tidal friction would have faded before synchronization completed. Instead, everything aligned: the mass, the rotation rate, the orbital eccentricity, creating a gravitational resonance so precise it seems engineered. Dr. Maria Zuber from MIT and the Grail mission once said, "The moon's orbit is a fossil of formation. Its current motion tells the story of how chance settled into order. And that's where the line between coincidence and inevitability blurs. Gravity doesn't choose, it obeys mathematics. Yet sometimes mathematics produces outcomes that look almost deliberate. The synchronization between Earth and Moon is one of them, a state that minimizes energy, maximizes stability, and maintains balance over billions of years. Mathematically, This equilibrium is described by the tidal torque equation, where the gravitational potential of one body interacts with the deformation of another. As the Moon's tidal bulges aligned with Earth's pull, the torque drove rotation and orbit toward a common rhythm. The energy lost in this process, once tens of terawatts, now manifests as small tidal shifts, and the Moon's steady drift outward, about 3.8 centimeters per year, confirmed by laser reflectors from the Apollo missions. Every centimeter of that distance is a record of energy exchanged, a cosmic ledger written in orbital mechanics. The key, scientists say, is the timescale. For a tidal lock to occur, the system must remain dynamically stable for billions of years. That requires not just gravitational strength, but also thermal evolution. The internal structure of the Moon must cool and solidify at just the right pace to support the lock. Data from NASA's Grail and LRO missions reveal that the Moon's crust thickened unevenly during this process, reinforcing the asymmetry that helps keep one side permanently facing Earth. It's a self-reinforcing system. Gravity shaped the crust, and the crust in turn stabilized the gravity field. This is why many scientists now refer to the Earth-Moon pair as a gravitationally coupled binary rather than a traditional planet-moon system. Its behavior follows the same physical rules, but its precision stands apart. Even in the outer solar system, no other pair mirrors this exact relationship. Pluto and Charon come closest. They orbit a common center of mass located outside both bodies, each locked to the other. But their small size and distant orbit make their tidal interactions slower, weaker, and colder. The Earth-Moon system, by contrast, is vibrant and dynamic. Tides flow, energy moves, and the balance remains alive. Statistically, the odds of this configuration forming naturally are low, but not zero. And in the language of physics, unlikely still means inevitable given enough time. The early solar system was a theatre of chaos, impacts, collisions, migrations of planets and asteroids. Within that chaos, billions of combinations of mass and momentum played out. Somewhere, one of those combinations produced us, a planet with a moon just large enough, just close enough, to stabilize its climate and allow life to persist. As Dr. Neil deGrasse Tyson once remarked, the universe is under no obligation to make sense to you. And yet, when we see the precision of the Earth-Moon lock, it almost does. The synchrony we see now, one orbit, one rotation, one luminous face, is not the result of design, but of nature's relentless push toward equilibrium. It's what happens when chaos has time to rest. Gravity, over billions of years, seeks the configuration that wastes the least energy, that moves the slowest, that endures the longest. The lock between Earth and Moon is simply the calm after the storm. Still, it's hard not to marvel at how perfect it looks from here. The Moon's apparent size in our sky almost exactly matches the Sun's, allowing for total solar eclipses, another numerical coincidence so precise that it seems intentional. Yet it too is just geometry, timing, and physics. The deeper we study it, the more the boundary between chance and necessity dissolves. Today, simulations from NASA's Ames Research Center and ESA's Gaia data confirm that such synchrony will persist for billions of years to come. The lock is self-stabilizing. Any disturbance, like a small impact or internal shift, generates restoring torques that return the Moon to alignment. It's as if gravity has written its own rule of balance, and the Earth-Moon system obeys it perfectly. Dr. Jack Lissauer summed it up best in his 2021 study on orbital resonances. The beauty of the Moon's motion is not in its rarity, but in how nature finds harmony in randomness. And so what seems like design is, in truth, the inevitable outcome of time and gravity, the twin architects of order in an unruly cosmos. The Earth and Moon, locked in their silent waltz, are not miracles. Their mathematics played out with cosmic precision. The moon looks calm, but it was born from chaos. Every crater, every ridge, every grain of dust on its surface is a fossil of impact, a memory of heat and violence. Yet behind that stillness lies one of the most cataclysmic events in Earth's history, the Thea impact, a collision so powerful it nearly destroyed our planet, but instead created its quietest companion. Around 4.5 billion years ago, the early solar system was still a battlefield. The planets were newborns, molten, unstable, surrounded by debris from the birth of the Sun. Earth at that time was barely recognizable, smaller, hotter, and still forming. Then came Thea, a protoplanet roughly the size of Mars, on a slightly inclined orbit that crossed Earth's path. According to simulations conducted by NASA's Ames Research Center and Harvard's Origins of Life initiative, they struck Earth at a shallow angle, traveling at about 9 kilometers per second, fast enough to melt crust, vaporize rock, and fuse the two worlds for a brief, blinding instant. The collision released energy equivalent to 10 to the 29th joules, more than enough to reshape both bodies. The impact ejected trillions of tons of molten rock into orbit. Some of that debris escaped into space, but most remained bound by gravity, forming a glowing disk of vaporized silicate and metal around Earth. Over time, perhaps within just a few thousand years, this disk cooled and coalesced into what would become the Moon. NASA's Lunar and Planetary Institute describes this as the greatest recycling event in planetary history. The Moon is, in a sense, made of Earth, and Earth, ever since, has been missing a piece of itself. Dr. Robin Canup, one of the leading researchers on the Thea hypothesis, summarized it perfectly. The Moon is what happens when a planet tries to heal. But that healing was anything but peaceful. After the impact, both Earth and the new Moon were red hot, wrapped in thick clouds of rock vapor. As they cooled, their mutual gravity began to reshape each other. Earth's rotation then, far faster than it is today, caused the newborn Moon to orbit at just 22,000 kilometers from the surface, a distance so close that it would have appeared enormous in the sky. At that proximity, tidal forces between the two worlds were immense. Earth's gravity stretched the young Moon, creating tidal bulges that deformed its molten crust. Meanwhile, the Moon's own gravitational pull tugged back on Earth, slowing our rotation. This tug-of-war transferred angular momentum from Earth's spin to the Moon's orbit, pushing it outward and gradually stabilizing its rotation. This is how the path from violence to balance began, a process that took hundreds of millions of years. The fiery energy of impact transformed into motion, then into rhythm. From chaos came synchrony. The mechanics are exact. The conservation of angular momentum, the most fundamental law of rotational systems, demanded that as Earth's rotation slowed, the Moon's orbital distance increased. What began as a searing molten aftermath evolved into a double-world system, with each body shaping the other's motion until they reached equilibrium. Modern evidence supports this sequence. Samples collected by the Apollo missions show that the Moon's isotopic composition, particularly the ratios of oxygen-16 and oxygen-18, are nearly identical to Earth's mantle. This tells us the two share the same origin. The Moon isn't a captured asteroid or a foreign body. It's made of Earth's own material, reforged by impact. In 2022, a team at NASA's Goddard Space Flight Center used new high-resolution models of the Thea collision to propose an even more dramatic variant, the synestia model. In this version, the impact created not just a disk, but a massive rotating donut-shaped cloud of molten rock and vapor called a synestia, within which the Moon condensed while still partially embedded inside Earth's extended atmosphere. The model explains the near-perfect isotopic match between the two worlds. Dr. Sarah Stewart, who helped pioneer the synestia theory, explains, "The moon didn't form next to the Earth, it formed within it. The boundary between them was blurred for thousands of years. When viewed through that lens, the moon's stillness today is even more remarkable. The system that began with vaporized rock and searing heat has, over billions of years, cooled into one of the most stable orbits in the solar system. What was once a collision of worlds became a gravitational partnership so precise that it maintains near-perfect balance. NASA's Lunar Science and Exploration program calls it a dynamic equilibrium, the same principle that governs star formation, galaxy rotation, and even the balance of forces within atoms. It's nature's most universal pattern, energy transforming into order. The moon's current synchronous rotation, always showing one face, is the final stage of that process. As tidal friction drained rotational energy, the system settled into the lowest energy configuration possible. The Earth-Moon pair became locked in rhythm, orbit and spin aligned. The violence of creation ended in silence, but that silence still carries traces of its origin. Beneath the moon's crust, seismic data from the Apollo passive seismic experiments show evidence of deep fractures, possibly remnants of internal differentiation caused by early tidal heating. NASA's Grail mission later mapped density anomalies in the lunar crust that correspond to those stress patterns, confirming that the moon's structure still bears the scars of its formation. Dr. Maria Zuber, principal investigator of Grail, noted, "The moon's gravity field is a record of its past. It remembers every force that ever acted on it. Indeed, the asymmetry between the near and far sides of the moon, the thinner crust facing Earth, and the thicker crust on the far side likely dates back to the Thea impact. The heat of Earth's still molten surface may have radiated toward the near side, keeping it warmer for longer and affecting how its crust solidified. That subtle temperature difference, locked in billions of years ago, still defines the moon's face today. This connection between destruction and harmony is not unique. We see it everywhere in the cosmos. Planetary systems form from collapsing gas clouds. Stars are born from turbulence. Galaxies stabilize after collisions. The Earth-Moon system is simply one local example of the same universal process. Disorder organizing itself through gravity and time. If you were to replay that ancient impact in slow motion, the sequence would look eerily familiar. Chaos, compression, expansion, equilibrium. The same pattern governs fusion inside stars and even the chemical bonding of molecules. Energy seeks balance, and when it finds it, stillness is the visible result. In this way, the moon's silence isn't hiding its origin. It is its origin, transformed. The calm face we see at night is the afterglow of violence resolved, the fossil of an ancient thermodynamic negotiation between motion and rest. The proof of its fiery birth is not gone. It's embedded in every orbit, every wobble, every tide that still connects it to Earth. As Dr. Neil deGrasse Tyson once said, "The moon is a witness not of peace, but of the moment when Earth learned how to keep time." Through the moon, we can trace the history of balance itself. Every tidal pulse, every measured drift, every shadow cast on its surface is a continuation of that first collision. From that single violent act came not only our satellite but the conditions that make our world livable: stabilized climate, predictable seasons, and the steady rhythm of the tides. It's no exaggeration to say that without Thea, there would be no Earth as we know it, and perhaps no life to wonder about it. So when we look at the moon's serene glow tonight, what we're really seeing is the fossil light of a catastrophe long cooled. Its stillness is not absence of motion, but perfection of balance, reached only through unimaginable energy. One day, Earth's rotation will slow so much that a single day will last an entire month. The oceans will no longer rise and fall in their familiar rhythm, and in the silent sky above, the moon will hover motionless, forever fixed above one side of our planet. That is not science fiction. It's the final stage of a slow, ongoing process that began the moment the moon was born. Right now, the moon is drifting away from Earth at about 3.8 centimeters per year, a distance confirmed by NASA's lunar laser ranging experiments, which have tracked the reflection of light from the Apollo reflectors for over 50 years. This gradual retreat is driven by tidal friction, the same invisible mechanism that once locked the moon's rotation. But the process hasn't ended. Energy is still being exchanged between Earth's spin and the moon's orbit, quietly, relentlessly, through every tide that rolls across our planet. To understand where this ends, we have to follow the mathematics of orbital evolution. As Earth rotates, its tidal bulges, created by the moon's gravity, are slightly misaligned with the moon's position in the sky. This misalignment pulls the moon forward in its orbit, giving it extra angular momentum, which makes it drift outward. Meanwhile, Earth's own rotation slows. The conservation of angular momentum demands balance. What the moon gains, Earth must lose. Dr. James O'Donoghue, a planetary scientist formerly with NASA, explains, it's like a cosmic seesaw. Earth gives away rotation. The moon takes distance. Both are heading toward equilibrium. That equilibrium point has a name: mutual tidal locking. It's when both bodies rotate at the same rate, Earth's day becomes equal to the moon's orbital period. In that distant future, one hemisphere of Earth will always face the moon, while the other will never see it again. Using NASA's orbital dynamics models, scientists estimate this could occur in 50 billion years, long after the Sun expands into a red giant and transforms both worlds beyond recognition. But purely as a gravitational system, the Earth-Moon pair will keep evolving toward that locked state until other cosmic forces intervene. At that point, a single day on Earth will last about 47 current Earth days, matching the Moon's month-long orbit. The tides will stop flowing. The oceans will settle. The energy exchange between the two bodies will end because the torque that drives it, the offset between Earth's rotation and the Moon's orbit, will disappear. Everything will slow to a standstill. For a while, the system will be perfectly balanced, but even balance in space doesn't last forever. ESA's Solar and Planetary Dynamics Division explains that as the Sun continues to evolve, its increasing luminosity and radiation pressure will alter Earth's orbit and spin. The Sun's own tidal effects, though tiny today, will eventually dominate, pulling both Earth and Moon outward as the solar mass decreases due to stellar winds. When the Sun becomes a red giant, about 5 billion years from now, its outer layers may expand enough to engulf Mercury and Venus and potentially destabilize the orbits of Earth and the Moon. If the Earth-Moon system survives that transformation, the pair may continue their dance in the dim outer orbit of a fading Sun, drifting together into mutual lock before the star collapses into a white dwarf. But the odds are uncertain. Some simulations suggest that before that happens, solar tides could slightly accelerate Earth's rotation again, disrupting the tidal balance and sending the Moon slowly drifting farther away. NASA's Astrophysics Division summarizes it this way: the Moon will not crash into Earth. It will drift outward until gravity, friction, and time reach a silent agreement. That agreement is not static. As the Moon moves outward, its orbital velocity decreases from the current 3,682 km per hour to slower and slower speeds. When the distance between Earth and the Moon doubles, their gravitational interaction weakens to just 1/4 its current strength. The tides we know, the twice-daily breathing of our oceans, will fade into minor ripples. Without tidal friction, many of Earth's natural processes would quiet down. Ocean circulation would slow, Climate regulation through the movement of heat across the planet would diminish. The gradual lengthening of the day, currently about 1.7 milliseconds per century, would cease. The system would reach gravitational rest. It would be the first time in 4.5 billion years that Earth and Moon have nothing left to exchange. But what if, before that point, the Moon escaped entirely? Astronomers say it's theoretically possible, though incredibly unlikely. To break free from Earth's gravity, the Moon would need to exceed its escape velocity, about 5,800 kilometers per hour relative to Earth. No known natural mechanism within the Earth-Moon system could provide that much energy. Even the gradual outward drift caused by tidal friction will never reach escape velocity. The forces weaken too quickly with distance. Instead, what's more probable is a kind of eternal companionship, a frozen dance. Over billions of years, the Moon will circle farther and farther away, its orbit widening until it settles into mutual lock with a slowly rotating Earth. Then the view from the Moon will change forever. Earth will stop rising and setting in its sky, becoming a stationary blue and white half-sphere suspended in space. From Earth's surface, too, the change will be profound. One side of the planet, the lunar side, will have the Moon permanently overhead. The other side will never see it again. Cities and continents that now share moonlit nights will part ways forever. The familiar rhythm of waxing and waning, of full moons and crescents, will end. The sky will lose one of its oldest clocks. Dr. Neil deGrasse Tyson described this future as a universe settling into stillness, not death, but equilibrium. That stillness isn't lifeless. It's the natural conclusion of motion, a balance reached after the long exchange of energy between two celestial bodies. Every system in the cosmos moves toward it, from galaxies to atoms. The Earth-Moon pair is no different. At that faraway time, if any observers still exist on what remains of Earth, they will see a moon locked forever above the same horizon. The same craters, the same Maria, frozen in the same position, the same silence unbroken. It will be the ultimate calm, the end of tides, the end of spin, the end of motion between two worlds. And perhaps that calm will reveal something we often forget, that what looks motionless is simply the end point of motion perfected. The Moon's stillness is not the absence of change, it is the completion of it. As NASA scientists often remind us, stillness in space is never absolute. It's just balance achieved. So will the Moon ever stop facing Earth? Yes, but only when Earth itself has slowed enough to face it back. Two worlds locked together, unmoving, orbiting as one. A day will last as long as a month. The tides will sleep. The sky will stand still. And when that day comes, perhaps the most accurate way to describe it will be this. We call the Moon still, but maybe, just maybe, it's the Earth that's slowly falling asleep. The Moon hangs in our night sky, a silent witness to billions of years of cosmic evolution. Its face, forever turned toward Earth, is not frozen by magic or chance, but by the patient, relentless work of gravity itself. Over 4.5 billion years, tidal forces have sculpted this perfect synchronization, transforming a rapidly spinning newborn world into the serene companion we see today. We've journeyed through the mathematics of tidal locking, explored the violent birth from the Thea impact, witnessed the hidden landscapes of the far side, and measured the ongoing drift that continues even now. We've imagined scenarios where this balance breaks and marveled at the subtle librations that remind us nothing in space is truly still. We've traced the invisible threads of gravitational conversation between Earth and Moon, a dialogue conducted in the language of angular momentum, energy dissipation, and orbital mechanics. What emerges from this exploration is a profound truth. The Moon's apparent stillness is, in fact, the most elegant motion of all. It is rotation and orbit perfectly matched, a dance refined by billions of years of gravitational negotiation. It is order emerging from chaos, stability arising from violence, and silence born from struggle. The same forces that created the moon from cosmic catastrophe now hold it in perfect balance, drifting slowly outward as Earth's days grow longer, both bodies moving inexorably toward a future of mutual lock. This is not a story of endings, but of transformations. The moon hasn't stopped moving. It has simply found its rhythm, a cosmic tempo set by the fundamental laws of physics. And in that rhythm, we find not just the history of our celestial companion, but a glimpse into the deeper patterns that govern all motion in the universe. Every tide that touches our shores, every shadow that crosses the moon's surface, every millimetre of drift measured by laser light, all of it tells the same story. That gravity, given enough time, always finds balance. The next time you look up at that familiar face in the night sky, remember, you're not seeing stillness. You're witnessing perfection, the culmination of 4.5 billion years of motion refined into harmony. The moon doesn't spin, or rather, it spins exactly as much as it needs to, locked in a gravitational embrace that has shaped our world and will continue to do so for billions of years to come. If tonight's journey through the mechanics of the moon's motion has brought you a moment of wonder or a deeper appreciation for the cosmos, I'm grateful you chose to share it here. A like or subscription helps this channel continue exploring these quiet mysteries of space and time. And I'd love to hear from you. Where in the world are you watching the moon tonight? Your thoughts and reflections, whether brief or detailed, remind me why these explorations matter. Until our next voyage through the cosmos, look up with new eyes and remember that even in apparent stillness, the universe is always moving, always dancing, always reaching toward balance.